All right, thank you very much, Jonathan. Thank the organizers. This is very, very exciting. I hope that a few years from now we'll look back on this day as when everything really got started in the AI space. I also want to give a quick note to Charles and his work. We converged on the name memory machines a few weeks ago, and it turns out that he's been using memory machines for many, many years. But anyway, we'll get to that. I want to talk about the memory singularity and perhaps give you a little bit of a different perspective on how we are thinking about memory. Together with Sharon, Sven, and Madame, who are here in the audience and are the true architects of everything that I'm going to be talking about. So humans forget. We forget things every day, and our key goal is to augment human cognition. And the memory singularity, I think we're not that far from the notion that very, very soon we will be able to actually remember everything. And that's our goal at memory machines. So first of all, and this was basically stated several times already, you are your memories. Charles already said it at the beginning of the morning, and this is who you are, basically. So if I ask you about give me a recommendation for a good restaurant, or if you think about the code that you've been writing, or what you're going to do tomorrow, this is the very essence of who you are. And loss of memory is devastating, both for the person themselves as well as for the loved ones. But memory loss is not just restricted to old people. It turns out that all of us forget things constantly. In fact, there are many quantitative studies that argue that we forget a huge amount of the information that we interact with on a daily basis. So it turns out that the word forgetting is a little bit of a misnomer. Sometimes we really forget things. There are things that really disappear. But oftentimes the information is in our brains. It's just that we cannot recall it. So the key problem in memory is about being able to recall that information. And if I can trigger that information in you, then our key argument is that we will be able to augment your cognition and help you truly remember everything. So I'd like to spend a few minutes now with something that's a little bit different from what we're normally used to, which is telling you about what we know about how our brains encode and retrieve memories. And there have been many people that have been working for decades trying to understand at the behavioral level what we do remember and what we forget, and also the mechanisms, actually the neural circuit mechanisms that orchestrate what we remember or not. So I'll give you a quick glimpse on that with two brief vignettes on this problem. So the first one, I'll tell you about neurons in a particular part of the brain called the human medial temporal lobe. Many of you may have heard about the hippocampus. If you don't have the hippocampi in both hemispheres, it turns out that you cannot consolidate memory. So I'll tell you what neurons do and how they represent information with a very quick experiment where we showed people short video clips, and then they were exposed to these different videos that had different orders. And I'll tell you about how the brain encodes one of the fundamental aspects of memory, which is the temporal order, the sequence with which things happen. So we show these video clips to people, and then we ask them in two different tasks what they remember and what they forget. One is a scene recognition task. Have you seen this scene before, yes or no? Or we show you two frames and say which one happened before. And we did this work with patients that have epilepsy, that have electrodes implanted in their brains. And this allowed us to get a unique glimpse with unprecedented spatio-temporal resolution to record the activity of individual neurons. So we can look at the individual fundamental components of memory in the human brain. So let me give you a quick glimpse of what happens in the brain when we are trying to remember short snippets of the video. So what you're seeing here, many of you may not be familiar with this format. Each of the tiny dots over there corresponds to the action potential, that is the fundamental unit of activity of a neuron in the hippocampus of one of these patients, while they're looking at the first event, order one, in one of these movies, okay? And so you see that this neuron was activated after that dashed line, which corresponds to the onset of a new event in memory. When we look at other events, event on number 2, event number 3, this neuron was not activated at all. And similarly, we have other neurons that represent order 2, order 3, etc. So here's the fundamental mechanism by which the brain can encode the sequential order by which things happen. And this is, I just give you a few examples. Here's a whole population of neurons. Some neurons encode what happens first, what happens next, etc. So there are fundamental units in the brain that are encoding the temporal order in which things happen. So this is the kind of inspiration that goes behind some of the algorithms that we're building to represent the fundamental structures of memory based on neuroscience. I'll jump gears now to another vignette where we studied what people do and do not remember. And this was a behavioral study where we built very simple machine learning algorithms to actually predict what people will remember or not under different circumstances. So in one of these experiments, we had people watch a TV series, in this particular case, a TV series called 24, and we registered with very high resolution basically every part of the movie, what people do or do not remember at different time points after watching this TV series. So what you're looking at here is a particular fragment of that movie from one of the episodes of this TV series from frame 55,000 to 56,000 or so. And each of the ticks corresponds to one particular event and whether people do remember that or not. This is participant 51. Here are 51 participants. And you can see that there's a huge amount of consistency from one participant to another in terms of what they remember or not. So here, in this case, this is the average across different participants. This is for another episode. And so we can measure very densely what will be remembered and what will be forgotten. And then we can build basic AI models to predict what's memorable or not. This is basically, I won't go into a lot of the details, but basically this is a combination of computer vision, language, trying to decode from the content and predict exactly what will be remembered or not. Here we can predict with about 75% accuracy for a single event and for a single person what's memorable and what isn't memorable. So back to trying to build algorithms that will augment human cognition. The first step is building what we call the memorome. The memorome is the complete organized record of an individual's memory. It's like a genome, but containing all your memories. So think about every conversation you've ever had, every person you've ever met, every email you've written, every book, every movie, everything is part of your memorome. We want to be able to encode that, and we want to be able to encode that in a way that is inspired by what we understand about the mechanisms by which the brain and people actually encode information. So this has to be multimodal. We extract all of the experiences from all the sources. In principle, we'd like to incorporate every single file, everything that's digital, incorporated into the memory. And one thing that I want to emphasize and talk a little bit more about now, and this was alluded to in some of the previous talks, is that we need new ways of evaluating human-like memory. And I look forward to seeing, where was it, in the previous talk from Tanka, the new benchmark that they have created. I think creating new benchmarks is essential for us to make progress in our field. And I'd like to invite our whole community to collaborate on that. So perhaps I'm preaching to the converted here. Many of you are probably familiar with the story of computer vision. MNIST was quite exciting, you know, it sort of started the whole discussion. But I think in the memory field, we are kind of in the pre-MNIST stage in terms of how we are evaluating memories. So ImageNet, with all the caveats, we can criticize ImageNet in a lot of ways, but ImageNet has been quite transformative in terms of being able to push the frontiers of computer vision. And that sort of ignited a whole era that transforms sensory intelligence. So if we think about large language models, one of the reasons they have been so successful is because they've been able to capitalize on enormous amounts of data that they have been using for training. We just don't have that for LMMs. So LMMs are large memory models. That's what we're building. That's what many of you are interested in building as well. And to build large memory models, we need fundamental benchmarks and data sets that we can build upon. And so we'd like to invite all of you to collaborate with us if you're interested in building better data sets and benchmarks for human-like memory. And here's a basic desiderata of what those benchmarks should look like. So first of all, we need to have access to ground truth. They need to be personal. We're in particular interested, in our case, in human memory, not in memory for agents, but actually in augmenting human cognition. They need to be able to incorporate time and be dynamic and incorporate the changes over time that are fundamental to memory. They need to be accessible, so I cannot quite share my entire personal history with everyone, so we need memoromes that are accessible for testing for the entire community. And importantly, they have to be large, right? So we cannot work with a data set that has, 100 snippets of conversation and then few questions and answers on that. So here's a couple of things that we're developing. One is the Abraham Lincoln memorome. Another one is celebrity-based memoromes, personal-based memoromes, and fundamental list of extensive questions and answers that we can all test our algorithms on. So we're going to be submitting a proposal for a NeurIPS workshop on benchmarks for memory, and would like to invite everyone who's interested in collaborating with us on this. I think this is going to benefit all of us. First of all, in defining what data sets we need for training models. Second, in evaluating rigorous benchmarks that we can all then compare notes with. So just to close, our vision is to endow humans with perfect and infinite memory. We want to augment human cognition. We want to make you superhuman. And to go back to the title, we think that we're not very far from what I call the memory singularity. Perhaps it's a bit grandiose to put that on par with penicillin, the DNA double helix, and the moon landing. But I do think that all of our lives and the world will be transformed in a fundamental way, the day we can actually truly remember everything. And I think that we actually have the tools to build that and to allow and enable all of you to remember absolutely everything. Here's part of our team, half of which is actually here, and I'd like to encourage all of you to talk to them, and I'll stop there. So thank you.